Welcome to Maths with EJD. In this video, we'll be talking about power sets and universal sets. So straight up, let's go and talk about them. The first thing we're talking about, of course, is power sets. Power sets, all right? And you should know that the power set of a set A, the power set of a set A is the set of all possible sets. Is the set of all possible subset rather, the set of all possible subsets of A, including including the empty sets, and A itself and A itself. Now, this is a very important concept. So the power set of a set is actually the set of all possible subsets of A, including the empty set and A itself. So the power set is denoted, the power set is denoted as P of A, So let's see some examples. First example, if A is equal to 1, 2, if A is 1, 2, then the power set of A, which is given as PA, is actually the collection of the empty sets, all right? Then the set containing only 1, the set containing only 2, the set containing 1 and 2. And that is the power set. So you see, empty set and A are involved, and then you have all these ones in between. All right. So the power set of 1, 2 is all this. Now, let's do something more. 2 now, you have that B. Okay, let me put it this way. If B now is equal to A, B, C, all right, that is B. So what is the power set of B? You can say then the power set of B is actually the empty set, all right, the empty set, then the set containing only A, the set containing only B. I mean, this is going to be a lot. But it's okay. So the set containing only B, the set containing only C. Then now you have to take them in pairs. The set containing AB, the set containing AC, the set containing BC. After taking them in pairs, then you can now take the final thing. So the set containing A, B, C, all that. So this is the empty set. This is B itself, and then everything in between. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if B is A, B, C, then the power set of B is the set of all the subsets of B. Now, there's a very important thing that you need to pay attention to. It is the fact that the number of elements, the number of elements in the power set of a set with a set with n elements is usually 2 raised to power n. So the cardinality of the power set of a set is 2 raised to power the cardinality of that set. Okay, that's a lot of English, but I'm going to explain it better after now. So if you remember A, right? Set A had 1, 2. And then you can see that the power set, so the cardinality of A is actually 2 because it contains 2 elements. But what happens to the cardinality of the power set of A? The cardinality of the power set of A is actually 2 raised to power the cardinality of A itself, which is 2 raised to power 2, and that is 4. And that is why, the power set of A actually contains 4 elements. The empty set, only 1. The set containing only 1, the set containing only 2, and A itself, that's 1, 2. So you can see that this is 1, 2, 3, 4. That's why the cardinality is actually 4. So that is to tell us that for B that has elements A, B, and C, okay, whose cardinality is actually 3, that simply means that the cardinality of the power set of B would be 2 raised to power the cardinality of 3. I mean, the cardinality of B, sorry, the cardinality of B, and that is 2 raised to power 3, which is 8. And if you go back to the power set of A, remember you had 1, 2, 3, 4, 5, 6, 7, 8 subsets. So that's a very important thing. So if I can simply ask you, a set contains 10 elements. What is the cardinality of its power set? You just know that is 2 raised to power 10, simply. Okay? Like that. So that is about power set. Okay? So, I mean, for the sake of more examples, let me give maybe more examples. Another set example, if I say 3 and I say C is X, Y, Z, all right? We already know that this is going to contain. So now that you know that rule, you can easily, or let me do something very, let me stress myself a bit. And I say W, X, Y, Z. So I already know that because the cardinality of C is 4, the cardinality of the power set of C is going to be 2 raised to power 4, which is 16. So for C now, the power set of C is going to be the empty set, W alone, X alone, all right, X alone, Y alone, Z alone. Then after so you take the empty one, you take them in ones. Then the next thing, you can take them in twos. You take WX. You know, you can be very strategic about this. You can take WX, WY, WZ, okay? And then after taking W, you can also go ahead and take X, Y. You take, of course, you already know order doesn't matter. So WX is XW, so you don't repeat that. So you have XY, you have XZ, and of course, you also have YZ. That's taking them in twos. After taking them in twos, then you want to take them in threes, okay? Want to take them in threes. That's W, X, Y. Then you have W, X, W, X, Z, W, X, Z. Then you also want to have W, W, Y, Z. And then after taking that, you can say, yeah, I think those are the possibilities you can have in 3. So how many do we have already? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, 12, 13, 14. So we have 2 to go. I've taken WXY. I've taken, yeah, you can take X, Y, Z, which we have not taken. And after that, the only thing left is W, X, Y, Z. Now, if you do not know the cardinality based on the rule we have got before, it may be difficult for you to know that you have not completed, right? But because I know I'm expecting 16 elements for a set, 16 elements for the power set of a set that has 4 elements. So this way I can be sure that, oh, I have one more to go. So I can begin to rack my brain for that one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I'm very sure when I'm submitting this in an exam, I'm very sure I've done the right thing. So there's nothing to worry about. So don't forget that the cardinality of the power set of a set is actually 2 raised to power the cardinality of that original set. Very important. So one last example for power set still. What happens, if you have a set D, which is just a single thing containing 1. So the power set of D is simply going to be, of course, you know already that the cardinality of D is 1. So that means the cardinality of the power set of D is going to be 2 raised to power 1, which is simply 2. So it means that the cardinality, the power set of D is going to contain 2 elements, and that's simply the empty set and the set itself. So for every single thing, the cardinality of their power set is 2. That is the empty set and the singleton set itself. Okay, so that goes as a nice one to talk about. So let's talk about universal sets. So we've talked about power sets. Let's talk about universal sets. Universal sets. So the word universal probably already is giving you some ideas. So let's see what exactly that means. Okay. You need to understand that a universal set is a set that contains all the objects under consideration. So any object under consideration must be in the universal set. All the objects under consideration, typically denoted by U. Not really the U, So U like that, without anything attached. So you need to understand that every set in the given context, every set in the given context is a subset of the universal set. So really important. All right, so let's take examples. Right. Okay. So first example, if the universal set U represents all natural numbers. It represents all natural numbers. Natural numbers are infinite. So if it represents all natural numbers, then the set E, which is 246, is a subset of the universal set U, right? So that goes. Another example, if the universal set, okay, I'm already giving it a tail, which it doesn't have. If the universal set represents all students in a school, then a set F, which is equal to students, in grade 10 is automatically a subset of U, is a subset of U. Okay, let me make something more let me give an example that is more practical. Okay, so you have this now. So let's say you have set G. Set G is 1, 3, 5. You have set H, which is say 1, okay, let me say 2, 4, 6. Okay, you have set I, and set I is actually 1, 2, 3, 7. Okay, and then probably you have set J, which is say 2, 3, 5, 8, like that. Now, if these are sets under consideration, of course, none of them has been named the universal set. So if you're going to have a universal set, like we said already, if these are the sets under consideration, a universal set is a set that contains every element that you can find anywhere. So the universal set can be something like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So everything in the everything you can find anywhere else. So every set under consideration is a subset of the universal set, that in short. So 1, 3, 5, you find it here. 2, 4, 6, you find it here. 1, 2, 3, 7, you find it there. 2, 3, 5, 8, you find it there. So that is the idea of universal set rather. So okay, so that's with that we come to the end of this. Okay, yeah, we're going to be talking about Venn diagrams later. Okay, maybe I should just use this example. Let me just talk about Venn diagram representation briefly because we're still going to talk about it fully later. Okay, so um okay, I mean let me leave Venn diagram till when we talk about Venn diagram, so we don't I don't get to repeat that again. So that's the end of the video. If you have not subscribed, be sure to do that. Hit the notification bell so you can always get alerted each time a new video is released. Then of course be sure to comment, like, and share. See you.